All right, so today's lecture is about this problem called discrepancy minimization, which is an interesting topic in and of itself, but I partly chose it because of the second part, its connection to random walks, and also its connection to Gaussian random variables. So we'll get to kind of use some of the ideas to some extent that came up last class, but also bring back a lot of those fun and games we did with Gaussian random variables maybe a month ago. And just get practice with a lot of good stuff. So, blah, blah, blah. Here's all the things we have done before. We teach so many things. It's crazy. Okay. All right. So today then, so discrepancy minimization, and it's going to be a random walk algorithm. So it's going to maybe also offer a different perspective on random walks than usual. And it's also going to give us some practice manipulating Gaussian random variables and little linear algebra and stuff like that. So, all right, but the problem, this discrepancy minimization problem is very simple. There's many applications, but I won't go into them. Let me just focus on this simple problem. So I give you a system of sets and points. Okay, so whatever sets contain points. And my goal is to color the points so that every set has the same number of each color. So I'm coloring all the points red or blue so that every set has the same number of red and blue points. Okay, so it's sort of like a balanced resource allocation kind of problem. Okay, so your input might look like that. So the sets are sort of these dashed lines, and then the points are obviously the points. Now, it may very well be the case, for example, a set even has an odd number of points, and to get perfect balance is impossible. Okay, so we're going to turn this into an optimization problem where the goal is to get a coloring that's as balanced as possible. So we're going to define, the discrepancy of a set, once you color it, will be the difference between the number of blue points and the number of red points, the absolute difference. Okay, and you want that to be close to zero. So our goal is to minimize the maximum discrepancy over all the sets. Okay, so I want to color things to get kind of as balanced as possible. So I thought maybe to make sure we understand the definition, we can try to color these points together. Okay, so I'm going to one by one circle these points, and you're going to tell me whether you want it to be red or blue. And if you get it right, exactly right on your first try, I don't know, something good will happen. We'll cancel class or something. Okay, clearly there's nothing left to teach. All right, so but I think it's going to be hard to do in one shot. All right, so I'll start with the top left, and someone just shout out red or blue. Okay, I'll go here. Okay, I'm going to keep going along the top here. Red. Okay. So again, the goal is to keep the same number of red and blue across. So I'm just going to roughly go in rows, unless you guys would prefer something else. How about this point? Red? Okay, we'll do red. Up here. Up here, or down below. Come on, guys, we got a lot of points left. Just pick red or blue. All right, how about this one? All right, somehow you guys seem to agree. Okay. All right, moving to the next row. How about this on the left? A timid blue. Red. How about this one? I heard both. Blue wins, I guess. All right, how about this one? Oh, maybe I shouldn't obscure it. You should. Blue? I don't know. All right, how about this one? Red, blue. This is just to preserve the big one on top or something? Okay. All right, making some progress. So I'll go here. Are you guys going to get this? All right, how about this one? Oh. Uh-oh. Thank goodness for, oh no. Okay. Well, thank goodness for undo. What do you guys want for this? Blue, okay. How about this one? How about this one? All right, how about this one? Okay. How about this one? Okay. How about this? Which one? I think you have a couple more in that same set, so you can always change your mind. How about this one? How about this one? All right, how about this? Uh-oh. How about this? Okay. How about this? Oh my God, are you guys actually gonna solve this? All right. How about this one? Blue. And how about this? One red and two blue. Okay. Dang it. Did you guys actually solve this? Okay. All right. Let's check all the sets. Are there any of them unbalanced? That's not true, right? We come up with examples where it always gets it wrong. Uh, so I think this is perfectly balanced. Is that okay? Well, well done. All right, we'll cancel a class. Yeah, maybe I should put this on a midterm. You guys would have aced it. Okay. So this one does have a perfect balance coloring. This was the answer I came up with. Uh, of course, you gotta understand it's much easier to make a perfect balancing out of nowhere because I can put red and blue wherever I want than it is to start with the points there and then decide if it's red or blue. Apparently you guys figured it out anyway. Okay, but anyway, so you get the idea. You want to balance red or blue, and yeah, maybe I should have come up with a harder example. Okay, anyway, so that's the problem. Okay, so first of all, let me just briefly remind us the additive turn-off balance because we're about to use it again. That's this. It's going to be on the side. Okay. And what I want to do is I want to look at let's look at this sort of symmetric case where we have n sets and endpoints. Okay. And the question is, if I just randomly color everything red or blue, what will be the maximum discrepancy of online coloring of a random coloring? That's like not even a typo. That's just like a completely different word, isn't it? All right. So if I did a completely random coloring, what is the discrepancy I will get just from applying the additive bound? Square root. Log? We log something. Okay, so, okay. In other words, okay, so let's say, so what is, yeah, anyone want to try to guess what it might look like? N divided by 2 or so? N over 2? No. Well, okay. Uh, so one thing we can try to do is maybe we can, okay, let's just guess. Let's just call this lambda, okay? And then see if maybe we can use turn-off bound to say, okay, what are the probability of it being at most lambda, and see also how big I need to make lambda to be so I can take the union bound over everything. Okay, so we'll just leave lambda as a variable. So if I said, okay, the probability that I guess the discrepancy of a particular set, I'll call it Si, is bigger than lambda. Okay, so maybe here's a good question for you guys. If I wanted to apply the additive turn-off bound and stuff, then I kind of want to turn this into a numerical thing, whereas we've been kind of talking about red and blue. So how might I model it? Yeah, we can make red 0 and blue 1. I'm going to do something only slightly different because it'll prepare us for the rest of the lecture, which is I'm going to say red is -1 and blue is 0. So on average it's 0, which is kind of nice because on average it's kind of not particularly red or not particularly blue because it's red or blue, right? So maybe we can write like we can have variables x1 through xn, okay, where xi is equal to let's say 1 if first the ith point, I shouldn't have used I, so xj, if the jth point is in sj and red, -1 if that same point is in sj and blue, and otherwise 0. I mean 0 if it's not in the set at all. Okay. All right. So we're looking at the probability that the absolute value of the sum of these things is at least lambda. Okay. Now let me say two things. One is the additive turn-off bound. For simplicity, I said it was between 0 and 1, but we discussed how it's sort of translation invariant. If I subtracted 1 from everything, so it's between -1 and 0, the average would also go down by 1. And so everything just shifts down by 1 and nothing really changes because we're only looking at an additive error. Okay, so the fact that we're now doing -1 or 1 doesn't change it too much. Actually, the only real difference is that the difference is a magnitude of 2 instead of 1. Between 0 and 1, now we go from -1 to 1. So we're off by a factor of 2, but that's only going to change the constant in the exponent, so it's not too big a deal. Okay, so, all right, so to apply the additive turn-off, we need to have some understanding of the expected value. What's the expected value of x1 plus up through xn? 0. Okay, so good. So actually, this absolute value of x1 plus xn is also the same as the x1 plus xn minus the expectation. So it's like putting minus mu in there. Okay, so really we just have this plus epsilon. Okay, right. So to put it in the same form as we have over here, the exact same form, there would really be a divided n on both sides. Okay, and so that'll give us something like e to the negative. I think the 2 disappears because of that factor of 2 from before. Sorry. lambda squared n over n squared, because that's epsilon squared n. Okay, so these n's cancel out. Okay, so I'm left with e to the negative lambda squared over n. That's the odds of having say lambda more red than blue. Okay. Okay, so if I wanted to make lambda big enough so that I'll be able to union bound over all the sets and ultimately get a bound for all the sets simultaneously, what might I set lambda to be? Okay, so if lambda was square root n log n, maybe times 2 or something, then we'll get, negative 1 over n to the fourth or something like that, 4 because the 2 squared. Okay, there's no negative there, is there? Okay, so with very high probability, the discrepancy is not bigger than lambda for any particular set. There's only n sets, so we can take the union bound over all the sets and see that, okay, a random coloring with high probability will have discrepancy at most square root n log n or so. Okay, so square root n log n is sort of what you would get from, our relatively standard tool of the additive Chernoff bound. Okay, let me just briefly, for those who came in a little late, just quickly say that the problem we're solving is you're given a bunch of points and sets, and the goal is to assign all the points red or blue, so that what you want to do is you want to make the number of red or blue in each set as balanced as possible. So that the absolute difference is called the discrepancy. The goal is to minimize the maximum discrepancy. Okay, so additive Chernoff will give us roughly square root n log n. The question is, can you do better? That's the big question. And roughly, can you do better than this kind of union bound style argument? Okay, so that's where this result by Joel Spencer in 1985 comes in, who showed that you can actually get discrepancy square root n. Okay. And more generally, if you had m sets and n points where m is bigger than n, you would get like square root n log m over n. Okay, when m is equal to n, that of course disappears. But this was a totally mathematical paper, and the proof was existential in nature. There was no algorithm to find such a coloring. So that left open this big problem. Can we get an algorithm to get a square root n discrepancy coloring for n sets n points, or in general square root n log m over n? Okay. All right, so the sort of first breakthrough comes many years later in 2010. This is relatively recent in theory. Who using a technique called semi-definite programming. This is a generalization of linear programming that we haven't discussed as a class. Was able to get, at least for the n and n setting, the symmetric setting, this is just square root n, right? So Bonsall was able to recover the original Spencer result of square root n. The log factor is off by a little bit, but still, it's better than the additive Chernoff. Okay, so this was pretty exciting. And then just a couple of years later, that was cleaned up. The bounds were cleaned up to get, again, the proper square root log m over n. Okay, and it's this algorithm that we're going to talk about today because it's actually kind of a remarkably, in some ways, simple algorithm. I think there's going to be some new terminology for us, so it might come across as awkward, but modulo some kind of new vocabulary. If we were comfortable with the vocabulary, then the algorithm itself is relatively simple. I'll try to convince you of that. And so it's very nice. Okay, so this is only 2012. All right. So that's our goal, is to try to do this algorithm that gets square root n log m over n, this kind of very good discrepancy coloring. It would be more convincing if you guys hadn't solved that one together. You might think, who cares about square root n? I got 0. Okay. All right, so let me just set it up. All right, so notationally, we're going to have m sets S1 through Sm, they're all subsets of endpoints. Okay, and the goal is to minimize, overall integral vectors x, -1 plus 1 vectors x, to the absolute value of x over Si. So I'm using this as a shorthand to just sum over all the coordinates and Si the value of xj. Okay, so I'm going from red or blue to plus or minus 1 for the rest of the lecture. All right, so that's the goal. This looks awfully similar. It's like there must be a reason. Is there a reason? Okay, there's a reason. 2 slides later. Okay, so our goal is to get an integral coloring in the sense that all the coordinates are -1 or 1. But in an intermediate stage, we're going to kind of work with fractional coloring, so to speak. So what I mean is a vector x between -1 and 1, but can have fractional values. So 0.2 is kind of like 0.2 blue, so to speak. -0.2 is like 0.2 red, depending on what we chose -1 and 1 to be. Okay, so we're going to be working with a continuous sort of fractional coloring, and our goal is going to try to take a fractional coloring that at all times is sort of satisfying our discrepancy bounds and gradually make it more and more integral. Okay, and actually, we're never going to quite go all the way to 1, just for technical reasons. But our goal is roughly to get every coordinate to be very close to 1, say at least 1 minus epsilon, where epsilon is like 1 over n. Okay, 1 over n is arbitrary. We could have made 1 over poly n, just something very small and essentially negligible. We just need like a little bit of discrete space to kind of make the algorithm proper. So I'll say a coordinate is tight if it's very close to 1 in this sense. Otherwise, I'll say it's free. All right, so let me just first make this basic point. So suppose you have a vector x where all the coordinates are tight, so they're really close to 1, but not quite plus or minus 1. Okay. The claim is that we can turn x into an integral vector while only paying like a constant in the discrepancy. Okay, so you don't quite have the integral one yet, but all the coordinates are very close. I'm saying you can get the integral one, and you're only going to pay a 10 for each set, which is nothing compared to square root n anyway. Okay. All right, so how might I do this? So suppose I gave you a vector x where all the coordinates are tight. What would you do? What's the most natural thing? You can randomly round, but actually that's not the more natural thing. That's more natural because you've been here for a while. But if you hadn't taken this class, you would have actually done something even simpler. Yes, okay, so something's either really close to 1, I'll just make it 1, or it's really close to -1, and I'll make it -1. So let's let y kind of round x to sort of the nearest integral point. Okay, and if I wanted to look at the total balance of some vector y, right? Then we'll be summing over all the coordinates in that set, yj, right? And this is xj, plus or minus at most epsilon. Okay. So whatever, if we had put some, okay. So, okay, maybe each coordinate increases by epsilon or each coordinate decreases by epsilon. And there's at most n coordinates and epsilon's like 1 over n or something. Okay, so it's only going to change things by plus or minus 1, which is nothing between friends when we're worried about square root n type of scale. Okay, so nothing too deep here, just saying that, look, just getting everything tight, maybe not quite 1 or -1 is good enough. So I can just worry about that for the rest of the class. Okay, so now the goal is to sort of take we're going to start with an all zero coloring. Okay, And our goal roughly is to take the all zero and gradually, so the good thing about the all zero coloring is it has perfect balance, right? Every set has 0 red and 0 blue. That's fantastic. But of course, we're not coloring anything. So our goal is going to be gradually try to increase the magnitude of the coordinates so that each one approaches 1 or -1. Okay. And what's sort of interesting, so I think this goes back to Spencer's paper, but we're actually going to not try to color everything in one pass. Okay. So our first goal is actually just going to be, let's try to get a fractional coloring X that satisfies all the discrepancy bounds we want. So the discrepancy of each set should be at most square root n, fine, or times some logs. But also I want at least half of the coordinates to be tight. Okay, so I roughly want to figure out the color of at least half the points. And this is the lemma that we're going to spend most of our time on. I'm going to give a slightly more detailed version at the moment. But the high level idea is to just color half the points. The other points have some arbitrary fractional coloring. So that the discrepancy is at most square root n log m over n. Okay. And then so we're going to take this and we're going to get some high level algorithm where, at a high level, we sort of apply this, we color half of them, and then we're going to take those points and roughly take it out of the system. So we're going to just fix those colors for those points, take them out of the system, and then sort of try to partially color the rest, and each time decrease the number of points by half. That's basically what's going on. So until we can get kind of all the points tight and removed from the system, I'm going to keep partial coloring, partial coloring, partial coloring. And even at this high level, not all the math works out yet, so you should be a little dubious. But I can still point out, each iteration I'm going to hopefully get rid of half of the coordinates. So n is dropping by half each at a time. And each partial coloring at some level, I'm paying some kind of square root n-ish type penalty for each set. Okay? But one thing very nice is that each iteration I'm removing n over 2 coordinates. So the first iteration I pay roughly square root n. The next iteration I pay roughly square root n over 2. The next iteration I pay roughly square root n over 4. So actually the discrepancy I'm paying is a geometrically decreasing series, right? Because you have 1 over square root 2, 1 over 2. So you have a decreasing series. So all of that is just going to add up to big O square root n. Okay, so actually, if we can just sort of color half of them, because of the n sitting in the discrepancy bound, we'll kind of be able to get everything to collapse. Okay, I won't actually do the full proof of the second half because just doing the partial coloring is where everything is interesting and it's going to take plenty of time, I think. Okay, but let me give a slightly more detailed version of the partial coloring lemma that we're going to focus on. So the only difference here is that I've now allowed for sort of this starting point x0. Okay, and the real reason why we need this starting point x0 is because when I'm doing the iterative coloring, from the previous round of coloring, I sort of have some fractional colorings for the colors that weren't tight. So in one round of partial coloring, I figure out half of the vertices, and the other half have some values, between -1 and 1, some fractional values in the middle. And I can't totally throw them away because they were participating in the discrepancy bounds from the previous iteration. So to sort of carry over these values, that's why we now have this extra x0 starting point, and we kind of want to subtract that out. Okay, that's the main difference at a high level. So given x0, we're going to do an algorithm that's going to compute a fractional coloring x, so that sort of the discrepancy with respect to x minus x0 is at most square root n. This is only needed for the part where you take the partial coloring and turn it into a full coloring and everything adds up nicely, which I won't actually do. But so there's a technical thing. And also half of the coordinates with respect to x are tight. Okay. So the only difference is that I'm introducing this x0. If you wanted to think of x0 just being the all zero vector, that'll be fine for the sake of understanding what's going on. Okay, that would also be the case for the first iteration of the partial coloring. All right, so um, to this point, does it kind of make sense what we're trying to prove? I know I didn't give the full details how to go to partial coloring to the full coloring, but I promise you that's not the hard part. Okay. All right, so, all right, here comes sort of the algorithm. Okay, so let me copy this so I can draw a picture. Okay, so I'm going to let lambda just stand for this discrepancy bound we're going for, some constant times square root n, log m over n. Now look at this set P. This is a polytope. Okay, so P is, okay, these are the set of all fractional colorings that meets all the discrepancy bounds. Okay? And what I want to point out is that those discrepancy bounds, each of those is two inequalities, right? Because of the absolute value that turns into two normal inequalities. So it's really a bunch of linear inequalities. So you have this polytope P that, you know, in some high dimensional space is made of a bunch of these straight lines, right? Some of these straight lines is coming from like, x10 needs to be at least -1, right? And another one of these straight lines is saying, xsi needs to be at most lambda, where xsi again is summing x over si. Okay, so you get this very high dimensional polytope. This is not really a representative picture because it should really be high dimensional and very complicated and so on and so forth, right? And what the algorithm is going to do is it's going to start at some point x is equal to x0, which if you want, you can think of it as the all zero vector because that's what it will be for the first partial coloring. Okay, but it's going to start at some point in the middle. And roughly, we want to get to a point anywhere in this big polytope where half of the coordinates are almost integral. Okay, and so what's the algorithm going to do? It's going to go here, and okay, so at some level, what direction do I go? It's not clear, right? Okay, and we're going to do a completely random direction. Okay, so it can go anywhere. And it's going to particularly be generated by a Gaussian vector for every a Gaussian variable for every coordinate. Okay, and so what the walk will kind of do is sort of meander. You know, it's this kind of Brownian motion, right? And every once in a while, you're going to get close to a boundary. And you want to stay in P, right? Because P is saying you're satisfying all the discrepancy bounds and your colors are between -1 and 1. And what we do here is when we sort of get close to a boundary such as this, right? And this is a linear equation, right? What we're going to do is we're going to say, okay, that's a boundary I'm worried about. I'm about to break this boundary and I'm quite concerned about it. So what I'm going to do from now on is I'm going to say, okay, I'm going to say that from now on, my random steps always have to be orthogonal to this direction. So there's one linear equation that's bad, and everything has to be orthogonal to it from now on. Okay, so then you start kind of, it's not very compelling in 2 dimensions, but then the walk will thereafter kind of have to always be orthogonal to this boundary and never get closer to the boundary. And then maybe it'll pick up another boundary that's also close to. Now you have 2 boundaries that you're about to violate. And then you're going to adjust the random walk by saying, I'm going to make sure I'm always orthogonal to both of those boundaries. So yeah. Okay, yeah, good point. So, okay, I'm going to put the random walk in the subspace orthogonal to the constraint. Okay, I'll do some equations in a moment. But maybe the high level takeaway is this. When you approach one of these walls, I'm going to say roughly, so originally you have n degrees of freedom because you can go any direction you want. And if you run into one wall, then I'm going to say, okay, that's one direction roughly I can't go anymore. I'm going to remove 1 degree of freedom. I still have n minus 1 degrees of freedom. And now I'm working in sort of an n minus 1 dimensional space, which is making sure it'll never hurt the one constraint I'm worried about until I pick up another tight constraint. And I say, okay, I'm concerned about this one too. I'm going to make sure that I'm always working in the subspace that's orthogonal to these two bad linear constraints. That leaves n minus 2 degrees of freedom, and I'll do a Gaussian random walk in there, and so on and so forth. Okay, so that's going to be a high-level idea, but maybe once I give more details, I'll explain. And somehow we're going to argue two things. That we're only going to run into, like, at most n over 4 or n over 2 walls or something like that, or get close to them, so that you still have a lot of degrees of freedom. And then we're going to argue that as long as you have a lot of degrees of freedom, that'll force most of the coordinates to actually go towards 1 and -1. Yeah, that's sort of a high-level thing that's going on. I mean, there's a lot of kind of interesting ideas at play. I know right now it seems a little silly because it's just a picture. Yeah. Yeah, so okay, so good question. So there's two kinds of boundaries. So if I was approaching a boundary that's like, oh, x10 has to be at least -1, then when I say orthogonal to this constraint, what we're actually going to do is we're just going to freeze that coordinate. Say, okay, I can't affect x10 anymore. Okay, so that's simpler. If I'm running into something like xsi is less than equal to lambda, then I'm going to say that, okay, so let's say that I'm going from, so if I'm running into this constraint that xsi is less than equal to lambda, by orthogonal, I mean that if I'm going from, say, xt to xt plus 1, I'm going to say that I want to constrain my steps so that xt plus 1 of si is always equal to xt of si. Okay, so that's maybe better. I'm glad you poked at me. So if I'm running into one of the variable constraints, then I'm just going to freeze that coordinate for the rest of the time. I lose 1 degree of freedom. Okay. And if I run into one of the set constraints, I'm going to say, oh, I want to make sure the discrepancy of that set never changes. I'm going to force the xt plus 1 to be equal to xt of si from now on. Okay, that's just a one-dimensional subspace that I'm trying to avoid. So although it's not a nice and clean, simple direction like this coordinate set to equal 0, it's still really just removing one dimension away from the random walk. Okay, that's the high-level idea. So let me give some more details. Okay, so we're doing this random walk in P, and with high, we'll have to show, but we're going to show that with high probability all the points are going to be in P. Okay, and the details is that at every step, the difference, so xt minus 1 is the difference between one step and another, is going to be a Gaussian vector from an appropriate subspace of Rn. That subspace we're going to choose based on looking at where we are and figuring out what are the dangerous directions we want to avoid, and then sticking to a subspace that's relatively safe. Okay. All right, is there anything over here? That's right, okay. Okay, so that's the high-level idea of the algorithm. At some level, the algorithm is almost kind of intuitive. It's also kind of crazy to just do a random walk and assume somehow this is going to get you a solution, right? But at least the idea of like, okay, let's be careful around the constraints that are very tight is somewhat intuitive. Okay. All right, so we're going to need two lemmas about Gaussians. You've seen them before, so I won't prove them. Well, I'll explain the second one in a moment. The first one is just like, okay, if you have a Gaussian with a standard deviation like some sigma squared, what are the odds that the absolute value is at least 100 times the standard deviation, 100 times sigma? That's at most e to the negative 100 squared. Okay, so that we've sort of seen before. The next one is a little bit, looks obscure, but I will explain it. So one thing that's kind of going on is that each step is going to be some kind of Gaussian step, but at some level, how we choose the Gaussian, the subspace we work in, does depend on our previous choices, right? Because we're walking along and then we get close to some walls, and that's going to slightly alter the subspace that we're working in, okay? So really the technical statement is that the kth step, conditional on the previous steps, is a Gaussian. They're not like completely independent from each other, okay? However, it will come up that, when we do these smaller subspaces, it won't kind of increase the variance. It can only decrease the variance. That'll make more sense when it comes up. So at some level, you have these t steps that each one, conditional on the previous ones being done, behaves like a Gaussian with variance at most 1. And the question is, how does the sum of Gaussians behave? Or some of these iteratively conditional Gaussians behave? Now, previously, we're like, oh, the sum of independent Gaussians is a Gaussian, and we're just done. Okay, that's not exactly the case here. It's a sum where one step at a time it looks like a Gaussian. Okay, and you roughly get the same conclusion. This is as if you were just adding up the Gaussians. So the odds of it being bigger than lambda square root t, but this is assuming that each step has standard deviation 1. That means that the sum of t of them would have variance t. So this is lambda times sigma, so to speak, is at most e to the negative lambda squared. So even this sort of conditional Gaussian kind of thing, it's behaving a lot like just the sum of Gaussians. It's a bit technical. If I hadn't pointed it out, you guys might not have even cared. But okay. So but roughly this is what you would get if they were independent Gaussians. That's the way to interpret this. The proof is very similar. You just have to be a little more careful to break them up. Okay. All right. So just some lemmas. I have them in the bottom right corner for whenever they come relevant. What am I supposed to do here? Let's see. Okay, that's right. Okay, so let me go in a little bit in some terminology. I guess we've already gone over this. So if I'm looking at the tth iteration, so I currently have xt at some point in my polytope, I'm going to say a coordinate is tight if it's close to 1 or negative 1. Okay. And similarly, I'm going to say that a set is tight if sort of the discrepancy is within epsilon of that bound I'm going for. Okay, so like we've already said before. All right. And then, based on that, I'm going to define sort of like a safe subspace with respect to y sub t. So these will be the set of vectors where the discrepancy over that set is equal to 0. Okay. And I want to point out that ysi is really a sum. So this is a linear equation in disguise. For any tight set, and that the coordinates equal to 0 for all tight coordinates. Okay, so if I move in a direction that's in the safe subspace, I'm not going to be affecting any of the tight coordinates or any of the tight sets. So if my change from xt to xt plus 1 lies in yt, then for all the tight sets, the change in discrepancy of si will be 0. And for all my tight coordinates, the change in the coordinate value will be 0. And then the other stuff, there may be chaos. Okay, so all the other stuff is just chaos going on. There's a lot of randomness. But whenever something gets dangerous to breaking the constraints within epsilon of breaking one of these constraints, I'll add it to my set of tight things, and I'll make sure my directions are going to kind of preserve and not test that boundary anymore. Okay. So going back to this algorithm, for each step t, I'm going to be choosing xt minus 1 to be a Gaussian vector from this subspace. And then I need to explain what it means to choose a Gaussian vector from a subspace. I'll do that in a moment. Okay, but at some level, the coordinates are going to sort of behave like Gaussian vectors. I mean, Gaussian random variables, whose variance are small. Except you're also going to be guaranteed that the difference, xt minus 1, is coming from this safe subspace, so that any of the tight constraints and coordinates won't be affected by the next step. That makes sense? All right, so what do I mean by sampling a Gaussian vector from yt, or how would I mechanically do it? Okay, so let's say yt has k dimensions. K is probably going to be close to n, but let's say it has k dimensions. Okay, so every single tight set and every single tight coordinate removes one dimension. It starts off with n, but then each linear equation subtracts one dimension and subtracts one. All right, so let's say C1 through Ck is an orthonormal basis for this subspace. Okay, so those are all n-dimensional vectors, but there's k of them. And look at this matrix that you put them in as columns. We're going to sample a Gaussian vector, a k-dimensional one, where each coordinate is a standard normal Gaussian. And then I'm going to apply u to g. Okay. So what that really is, or one way to think about it, is to write ug is going to be like, g1, c1 plus g2, c2 onto gk, ck. So it's a sum of this basis from this vector space, right? And it's a random sum where the coefficients are given by Gaussians. Okay, and that'll actually give you a random Gaussian from that subspace. Okay, so that might seem a little bit eccentric. So let me put up a few lemmas just some basics to get some comfort with what's going on mathematically. So the first is, let's look at this vector u. My claim is that u transpose of v will never increase the length of v. Does anyone know what u transpose does? So we can work it out mechanically. So what u transpose of v would do, okay, is it would produce, the ith coordinate is going to be the dot product of the ith column of u. So the columns of u become rows of v, right? So u transpose is looking like this. C1 is in the first row, C2 is in the second row, and so on, right? So when I'm applying V, right, that means like V1 is getting applied down here, V2's will kind of go down, right? So to produce the first coordinate of U transpose V, I'm really going to be taking the dot product of V and C1. To produce the second coordinate of U transpose V, I take the dot product of C2 and V. Okay? So what U transpose V is actually doing is it's actually projecting V into sort of the subspace spanned by C1 through CK and giving coordinates in the basis of C1 through CK. Okay, so C1 through CK is sort of a coordinate system for our subspace, and this operation is projecting V into the subspace and giving the corresponding coefficients. Okay, so projections never increase the length. But to make this 100% clear, if I wanted to look at the length of this squared, you would get the sum of I equals 1 to k of ci v squared, right? It's a sum of squares of the coordinates in that subspace, in that change of basis. Okay? Now, starting from C1 to CK, I can extend that to a orthonormal basis of the entire vector space, right? So I have the first k vectors, that's orthonormal, and I can turn that into a basis of all of Rn. So some subspace, now I have an orthonormal basis of everything. Okay? Now, I know that if I took V and I rewrote it in this new coordinate basis, I would get the same kind of sum of squares, right? I is equal to 1 of n, ci comma v squared. Okay, so what am I saying? C1 through ck gives an orthonormal basis of a smaller subspace, and I can extend that to an orthonormal basis of the entire space. Here, all I'm doing is I'm rewriting v in that coordinate basis and looking at the length in that change of coordinates. That would be the dot product of ci and v for all the i's. Whereas up here, utv squared is just the first k ones. So clearly this sum has some extra non-negative terms compared to this one. So this thing is at least that thing. Okay, fine. I don't know if this is obvious or if this is alien, and I suspect maybe there's a mix in the crowd. Great. Okay. Otherwise, take it as fact. Here's maybe something more interesting. Okay, our steps are going to look like UG, right? Where G is some Gaussian vector and U is this sort of matrix of orthonormal columns. So one way to try to understand what this behaves like is to say, okay, so UG is a vector. And if I took an arbitrary other vector V and I looked at the dot product, what does that look like as a random variable? The claim is that that'll look like a Gaussian with variance at most the norm squared of V. Okay, which was enough to sort of understand what we need out of UG. Okay, so how do we do this? All right. V UG, okay, is equal to U transpose V G. Nothing too big a deal. But what's nice about the right-hand side, right? Let's call this B, right? Just to make it extra clear. This is a sum of Gaussians with coefficients given by B, right? So I know that this is distributed as a Gaussian with variance equal to the length squared of B. This is all coming from that sort of Johnson-Linus-Strauss random projection discussion, okay? And B squared, the length of B I mean, which is U transpose V squared, which, as we previously discussed, U transpose does not increase the length of a vector because it's just projecting onto a smaller subspace. Okay. All right, good. So whatever. This might seem a little eccentric, like a lot of machinery, but this is roughly all we need to take away from this kind of thing. Okay. All right. Okay. So now we can sort of explain the algorithm a little better. So this T step is going to be doing this UG. I've annotated with T just so it's like the subspace corresponding to the T step or something. Times some small step size. So delta will be like epsilon over, I guess, polylog, but this could be as small as you want to make the analysis easy. You know, roughly square root log m over n is log mn is enough for the analysis to go through, but it doesn't really matter. And again, U is coming from what is the safe subspace. G is some random Gaussian of an appropriate dimension, and so delta is a small step size. Okay, so we need the step size to be small. How are we doing on time? Not good. All right, the first claim is if one step is already in P, then the next step is going to be in P. Okay. So anyone want to try to guess at a high level why this is true? Yeah. Yeah, okay, so one half of it is that everything that's within epsilon of a bound, every time I'm epsilon within a constraint, defining P, I freeze it, right? So that's safe. Now the only question is, so now I have some padding, epsilon padding. Now, what are the odds that a point here, jumps over the padding? That could happen, right? So, okay, so let's look at, if I look, for example, at xt minus, so let's take some set that's not tight yet. The tight stuff is going to be safe because those are completely frozen. But if I look at something like this, right, so how much does the discrepancy of a set change from one step to a next, assuming the set is not even tight? Okay, and this was equal to our kind of delta u, I guess it's annotated by the step, right? Si, so to speak. Okay, sort of using the same notation. It's looking a little awkward. But this thing, okay, is going to be some Gaussian random variable. Let me put it this way. This thing is a Gaussian random variable with variance at most 1. And so maybe I should just make this, okay. Let's just make delta very small, okay? So I'm doing a Gaussian times, I can think of SI as the indicator variable of SI, okay? So this whole thing is looking like a Gaussian with variance at most the size of SI, because that would be the L2 norm squared of the indicator variable of SI, okay? Which is at most n, okay? Okay, so what am I saying? I'm saying that the change in discrepancy of one of these sets is also like a Gaussian, because it's really multiplying a Gaussian against the indicator variable of that set, okay? Which is just summing up the Gaussians. All right, so this part looks like a Gaussian with variance at most n, and now we'll just make delta so small that overall it looks like a Gaussian with variance at most, I don't know, epsilon over n. So if I made delta like at most, epsilon over n squared or something, we can control the step size. It'll make the algorithm slower because we take more steps, but who cares? It's polynomial. Okay? The whole thing is going to look like a Gaussian with variance at most, I don't know, epsilon over n. Okay? Now our buffer was size epsilon. So the odds of something with variance epsilon over n being bigger than epsilon, now we can apply, this kind of thing here. The odds of being that many times bigger than your standard deviation is going to be e to the negative whatever. So the odds of jumping epsilon when the variance is epsilon over n is going to be like e to the negative n squared or something very, very small. Okay? So that's the second part of the answer. So the first part of the answer is that things that are already tight, we're freezing. And things that aren't tight, there's a buffer of epsilon. And each of those kind of constraints I'm worried about, the change looks like a Gaussian with variance, I don't know, 1 over poly m. Okay. So it'll never make that epsilon leap. Okay. That's plenty to do a union bound and all this stuff. So, okay, fine. And t is going to be like roughly 1 over delta squared, so it's going to be polynomial in n. So we have plenty of high probability stuff to take a union bound over all the steps and say, okay, all the steps are going to be in the polytope with high probability. Okay. All right, so that's good because that addresses the fact that, okay, at least I have a fractional coloring that's satisfying the discrepancy bounds at all times. The remaining issue is showing that half of the coordinates are going to be tight by the time I get to the tth iteration. That's the hard part. Still with me, mildly? Okay. Okay. All right, so at some level we're going to, if many of the coordinates are tight, that also means that the L2 norm is pretty big, right? The sum of squares, because everything is close to 1 and negative 1, is going to be pretty big. So that's what we're going to try to focus on, trying to show that the norm must be pretty big. Okay. Whew. All right. So here is sort of the next claim. The claim is, this is a random process, I can only talk about expectations. So let's look at the expected length of the last step, or after the last step. Okay. The claim is that it's at least delta squared times the dimension of each of those subsequent safe subspaces. Okay. Which is at least the last safe subspace. But this going from here to here, you guys might be able to guess right now. So why is it that roughly dimension of the last subspace is smaller than all of the previous subspaces? Yeah, okay, so as constraints get tight, the subspace gets smaller. And the constraints don't become untight later, they're just frozen. So as a result, the subspace is just getting smaller and smaller over the time. The dimension's always going down. Okay, so the last one will give you the smallest dimension. Okay, so how do we prove this? make sure I do okay. All right, how do we prove this? Okay, so let's look at one of these differences. So let's look at the difference, or let's just look at this, right? So this was taking the previous vector and adding this sort of like Gaussian thingy. Which is, to break it out, xt minus 1 squared plus the inner product, two of them, plus the length of that Gaussian thing. Sorry, ran out of space. Hopefully you guys can kind of guess what's supposed to be there. If I take the expectations of each of these things, right? Okay, so this one, that's fine. So 1 minus the other is not a big deal. What's the expectation of this inner product? 0. So again, this is a Gaussian vector. An inner product times a Gaussian vector is a sum of Gaussians, but everything is still mean 0. Right? So we still end up with a mean 0 Gaussian in this term. So this expectation is 0. So all we're concerned with is that right-hand term, which if I pull out the delta, is this. Okay. Okay, let me, for the sake of time, suppose I promise you that, so all U is doing is sort of taking your k-dimensional subspace and embedding in the n-dimensional space, but roughly nothing really changes, so to speak, right? You really have k coordinates fluctuating in a n-dimensional space. So I'm claiming that the length of this vector is going to be equal to the length of this vector, just like how, I don't know, if you had a line in one-dimensional space, it still has the same length in a bigger ambient two-dimensional space. Okay, so this is really a k-dimensional vector sitting in n-dimensional space. This is the underlying k-dimensional vector in its kind of original k-dimensional space. So the length will be the same. I'm skipping some math. But now we can answer this question, right? So this was a Gaussian vector from that subspace. What will be the expected length squared? Sorry? It's going to be dimension of yt, so you're going to get the variances all added up. So each of the coordinates, so each coordinate of this is a normal Gaussian with variance 1. Right? And then however many coordinates is just a dimension of the subspace. Okay. All right, lots of moving parts here. Okay. I think some of this will make more sense in a few weeks past when we get more used to the terminology. Right now, we're sort of getting used to some terminology at the same time. All right, good. We did a hard lemma. Here's where maybe things start to really get interesting. My sense of the word interesting. All right. All right, now this is what we really kind of want to start trying to prove. So after t iterations, I want to know what's the expected number of tight coordinates. The claim is that it's at least n times 1 minus 1 over delta squared t. This is an arbitrarily small constant because t will be some constant divided by delta squared, however big a constant I want to be. So arbitrarily small constant times n, so roughly n, minus the number of tight sets. This is sort of an interesting relation in and of itself, right? Here's the thing I want to analyze, and then somehow there's some dependency on the tight sets. At a high level, does anyone want to try to guess why there is a connection between tight coordinates and tight sets? Okay, so here's some high level ideas. If xt squared is really big, then many of the coordinates have to probably be tight. So if xt squared is very close to n, right, which is the maximum in some sense if you're staying in P, then many of the coordinates would have to be tight. But for that to be true, I need all of these dimensions to be big, to be racking up and getting a lot of distance, a lot of length, right? But if I had a lot of tight sets, these dimensions would suddenly become much smaller, okay? And I wouldn't be making progress on the length, and I wouldn't have a bunch of tight stuff. So at some level, if I don't have any tight sets, then I'm more likely to have more tight coordinates because those dimensions will be very big. Let's see that play out. Okay, so the first step required some justification, which I'm going to omit. It's not too hard to do. Okay, so we've shown that with high probability x of t is going to be in the polytope, in which case the length is definitely less than n. We haven't actually shown that the expected value is at most n, because maybe like every once rare moon, it'll be infinity length or something, but that won't happen. It's not hard to prove that inequality, but since we kind of have 5 minutes, I won't do that. All right, so let's take for granted that n is at least the expected length of the final one. Okay? And what we showed is that this thing is at least delta squared times t times the last safe subspace dimension. Okay? And this is at least, so you start off with n dimensions, and every time you have a tight set, you lose one dimension, or at most one dimension, assuming it's not linearly dependent with the previous sets. Okay? And every time you have a tight coordinate, you also lose one dimension, or at most one dimension. Okay? So if I start rearranging this, then you start getting like, okay, delta squared t times the number of tight j's is at least delta squared t minus 1 times n minus delta squared t, the number of tight si. I should be putting expected values around everything all over the place, and I forgot. But use your imaginations. Okay? Dreams come true. All right. So there's expectations around everything. And if I divide out the delta squared t, then we start to get exactly what we're looking for. And again, everything is in expectation. Okay, so there's some kind of relationship there. Okay, 4 minutes left. Some people have midterms. All right, so after that point, now our goal is to try to bound the number of tight sets SI. Right, that's what we've reduced it to. So let's see what's coming up. The claim is that this thing is going to be at most n over 4. Okay. All right, so does anyone you can actually guess at a high level why this might be true? Okay, so let's just look at a particular set, and I want to show that the odds of it being violated are small, and then we'll take some expectation at the end, linear of expectation. So for each set, the damage I'm doing, or the change in discrepancy, is a Gaussian random variable, okay, with variance at most 1 times the size of SI, dampened by the step size or something, but it's a Gaussian random. And over t steps, I'm really summing together t Gaussian random variables. So at some level, we'll be able to apply some concentration bounds to the full sum of changes to discrepancy. So that's where we're going to use one of these obscure lemmas about Gaussians, the one where that worked for the particular case where we had a sequence of Gaussians where each one conditional on the previous one looked like a Gaussian of some variance. Okay, so that's how we're going to try to analyze the change in discrepancy of each set. Okay, so, right? So we also bring into play, these things. So, okay. All right, so what's the point? So yt, which is equal to this difference, right, is the step jt, which is behaving like a Gaussian times si, okay, with mean 0 and variance at most delta squared times n. Okay, so the n is coming from the si, like before, and the delta, if you take a variable to multiply it by 10, that increases the variance by 100. It squares. Okay, so now when we analyze this kind of thing, right, and I look at the probability that it's bigger than lambda minus epsilon, or something like that. Okay, I'm going to, just to make my life easier, let's call this, I guess, lambda bar. So lambda bar is still equal to some constant times square root n log m over n, right? So if I subtract out epsilon, that's not really a big deal. I could always make my original constant c bigger, and that'll make c bar as big as I want. So nothing really changes. The minus epsilon is kind of irrelevant. Okay. So if I wanted to apply this lemma from before, where the variance is at most 1, okay, the normalized version would be dividing this thing by, okay, so we said the variance was delta squared n, so we'd be dividing by delta over square root n, and this thing would be divided by delta square root n. Okay, so if we apply this e to the negative lambda squared thing, we get e to the negative lambda bar squared over delta squared n times, there should be a square root t and divided by square root t. Okay, you just have to believe me. Okay, you'll get something like this, e to the negative lambda squared t over delta n, if I had a little more time to plug and play more carefully. Okay, okay, so what do we get? We get e to some constant squared times, I guess, t over delta squared, that's some constant that we get to choose, times, okay, so this thing's getting squared. We have an n log m over n divided by n. Okay, so this cancels out, and roughly whatever constant t over delta squared is, because t was some constant divided by delta squared, I can make c bar a little bit bigger to eliminate it. So we should get something like you know, whatever we wanted, but let's say n over m times 100 or something. Okay. All right. I guess 8 was what I thought was more appropriate. And now by linear expectation, we apply that to all the sets. You know, n over 8m times m will give you n over 8. Okay. We're almost done. I have one question for you guys. I know I'm 2 minutes over right now. Okay. So let me just explain where we are. So we've now shown that should be an 8. The expected number of tight sets is at most n over 8. Of course, that's conservative. We could have made it smaller by playing with constants. That means the expected number of tight coordinates is at least 3n over 4 if t is, I don't know, 8 over delta squared or something. All right, last question. I ultimately want to show that the number of tight coordinates is at least 1/2, that we colored half of the coordinates. And that'll end the lecture. Okay, I've shown the expected value is at least 3n over 4. Why does it have to be at least n over 2? And how would I prove it? Okay, so what would I apply Markov's to? How would I apply Markov's is the right answer. Ah, okay. So let's let I guess z be the number of free, which was the same as not tight coordinates. Okay, so number of free coordinates. So we know that, okay, so number of free plus number of tight makes n. So the expected number of free coordinates must be at most n over 4. Okay, so how do I apply Markov's inequality? To get what we need? Almost done. Okay, the odds of it having at least n over 2 free coordinates is at most 1/2. So it's probably 1/2. You have less than n over 2 free coordinates. That means you have at least n over 2 tight coordinates. That means you've colored half of the points. You have your partial coloring. We have our glorious lemma. For reasons not fully described here, the partial coloring will lead to a full coloring by iterating and choosing your x0 based on your previous iterations, partial colorings. Okay? That part's not nearly as hard as the stuff we did together. Okay, so that's the thing, and that's how you guys, yeah. So otherwise, the other algorithm is you do it by hand in a class of 20 students, and you always get a 0 discrepancy coloring apparently. Okay, all right, thanks guys.